So outside, so the poster session is absolutely fine according to regulations. We don't need to wear masks. The beach bar is absolutely fine. And if you feel symptoms, right, you need to inform the lobby, the reception. Every day from 12:30 to 1:30 there will be a doctor, so that you get a test, right? And if the test is positive, you need to stay 1 day after the test is positive in the hotel room, in the quarantine, so to speak. This is nice vacation, right? And if you want to have food, then you just give the reception before the night, and they always bring you food. Food. Nobody must behave to the rules, right? So the questions, that's basically it. I hope you're all be fine. Everybody's masked. So outside is absolutely fine. That's what the lady said. So you behave, you need a mask. Thank you very much. Hey, du musst auch noch fragen. Gibt es hier irgendwo Masken? Du musst in der Lobby fragen. Thank you very much. Now it's a pleasure. I hope it's a pleasure for you too. Jakob. Ja. FMS. Is the mic connected to the computer? What do we need to do with the Jakob camera? No. What can we do with the mic?
No, it's okay. Jakob even can hear us.
Jakob, can you hear us?
I can hear you.
Okay.
I hear you better than the others. I hear you.
Okay, good morning, ladies and gentlemen. It's a pity that we have to do this representation this way, because Jakob is about 200 meters from here, and it would be much more fun to have you in person. But I'm happy that technology is so far so good that we can do it at least in this kind of procedure. So the idea of this day was more or less the following. We thought that we should present some talks from people who have experience in industry, but in addition think about software in a more conceptual way. And we found 4 speakers, and 3 of them really meet this requirement. One of them does not meet this requirement, and some people start laughing because they have an idea who this one person is. And I don't go into more details now. Okay, but Jakob certainly belongs to those who have experience in industry. So he studied Latin and Greek, ancient Greek, and philosophy in Aarhus in Denmark, but later on he turned to computer science, and that is a very good idea. He was with Microsoft Research, he was at Stanford, and since 2006 he is a professor for informatics, software engineering in Dortmund, and in addition he was until recently the director of a Fraunhofer Institute, also in Dortmund, and Fraunhofer is really an applied institution. So, Jakob will talk about what will he talk about? How to automatically compose large systems from repositories of components. I think this is really a fundamental topic, and I'm very curious to listen to it. So please, Jakob, can you start?
Yes, I hope one can see my slide this morning.
Perfect.
I have done my screen sharing. I hope you can see my slide.
Wolfgang, you have to say yes?
Yes.
Yes, we can hear.
Yes, we can hear. Okay, so I'll just get started then. Well, thank you very much for the invitation to come here and speak to you. And yes, as you said, it would have been more fun under more normal circumstances, but that's the way it is. So let me just dive right in and talk about how to automatically compose larger systems from repositories and components. And in the talk, I'd like to try to force myself to really focus on applications of a framework for automatic composition of software from components for combinatorial logic synthesis. But I guess I have to start off by saying a little bit about what is combinatorial logic synthesis. I'm not going to try to cover all the ways in which the theory for this framework is sort of has been developed and what that all is. It's got in my mind, actually a fascinating theory. But I'll just give some pointers into that. Then I'll talk about the CLS framework and give you some idea of how that works. And then I'll try to spend most of the time, if I can force myself into the right discipline here, to talk about some of the applications that we've done. So combinatorial logic synthesis is something whose theory I developed about 10 years ago. And the idea was to try to deal with sort of some of the classical problems had to do with program synthesis. And around 2014, Moshe Bali and I did a Dutch group seminar that was devoted to the idea that instead of trying to do program synthesis, which is one of the hardest problems in sort of this area of computer science, instead of trying to do it from scratch, that is, you only have a specification and then you try to really construct the program bottom-up satisfying the specification, construct a system satisfying specification. We should really try to leave that idea because it's too hard. So what we should try to do instead is to say that we've got some components in the repository and we try to deal with a different question, namely the question, is it possible to compose a program from those given components that satisfies some sort of specification? The classical problem of synthesis is inherently difficult for two major reasons. One is the reason of computational complexity. And these problems tend to be super exponential. But the one that I find most important actually from the practical perspective is the problem which I mentioned, which I would call specification complexity. And so the idea of component-based synthesis is not least to the idea of trying to lower the complexity of specifications because we can rely on components that already embody some sort of design intelligence. And I mentioned that we did a Dutch group seminar back in 2014 on this. And my particular direction with CLS, with combinatorial logic synthesis, is to use type systems as a specification language for synthesis, but I'll get into more of that. I do want to mention, just now talking a little bit about the background for CLS, I need to tell you a little bit about what combinators are and what combinatorial logic is, because that's really at the heart of the way this thing works. And it has a nice logical theory, as I said, but I can't get into all topics pertaining to that here. I do want to mention that the whole thing goes back to the seminar that we did in 1920, when Moshe Schoenfinger, one of his PhD students, who then went to Moscow and died, and pretty soon after he went back to Moscow. And Schoenfinger wrote this paper, Über Bausteine der mathematischen Logik. And the one thing I want to direct your attention to here is the use of the word Baustein. Baustein is a building block. I think this is the first mention of the idea of constructing systems from building blocks in a logical sense. Okay, so with that, I just want to move on to see if I can get my slides moving. Combinators, you might know, if you've done computer science, not all of you may have done this sort of computer science, but if you have, you will know about the SK calculus. That's essentially what Schoenfinger did. He defined three functions called SK and I, and their definition is written here. These definitions say how these functions act on arguments x, y, z. And you can see you've got at the bottom you've got the identity operator I, the k operator is a projection operator, and the s operator is a sort of slightly complicated composition operator for functional applications. And we can give types to these things, and then it becomes a real logic. It becomes a fragmented intuitionistic propositional logic, but we don't have to care too much about that. But the fact that there are types for these combinators is an important fact. It turned out later that SK calculus is 200 complete. You can actually program any you can simulate a Turing machine using just these three functions. Now here I should say, I'm not so interested in here at all in the minimalistic approach that Schönfeld took. We use trying to figure out how few functions can I do everything that can be done. That's not my interest. My interest is the structural components that this theory gives rise to. And combinatorial logic in the simplest possible form, using so-called simple types that are just type variables or function type sigma arrow tau, means type of all functions from it takes arguments of type sigma gives back results of type tau. This system is so mind-bogglingly simple that you are sort of compelled to ask, could I possibly do anything interesting with that simple system? Combinatorial expressions themselves are trees, syntactically speaking, consisting of combinator symbols x, the green x up there, or generally applications of combinators to other combinators, so you can apply a combinator f to a combinator expression g. So syntactically speaking, that's important later on. Combinatorial expressions are just trees that have combinator symbols x at the leaves. The typing rules at the core of combinatorial logic are also so simple as to actually provoke the question, what good is that? Okay, so there are two rules. One says that if I have f in my assumptions that gamma is a set of type combinator symbols that I may use, and so here I have a combinator symbol x with type tau, that's an assumption. Later on, that will be a repository, actually. And then I can use that combinator symbol x at any substitution instance of tau. That's important. You can substitute type variables with types. And this is characteristic of what became known as Hilbert style logic, namely that actions in the Hilbert style logic are taken to be schematic. And the schematism of these logics is seen here, namely that actions or combinator types can be substituted into. And then there's a rule that type 2 function application, if a combinatorial expression f has type sigma arrow tau, and G has type sigma, well, then I can apply f to G and it has type tau. No surprise there. The basis for everything we do in CLS is to use the so-called typing computation problem in combinatorial logic as the foundation for automatically constructing compositions of combinators. And so this precision problem is formally given here. Given a type environment gamma containing type combinators like x colon tau before, and a goal type sigma, is it possible to construct a combinatorial term f from the combinators in gamma, from the repository gamma, such that f has the target type sigma? And so again, the basic idea is to regard this combinatory collection of type combinator symbols in the assumptions of gamma, and to think of that as a repository of component interfaces. So all we have at this level are component interfaces in the form of names, x, those are combinator names, they're just symbols. And then colon tau, meaning that this combinator symbol has interface type tau. And then what we try to do is simply to compose, functionally compose, these combinator symbols from gamma in such a way that the result is well typed at the target type sigma. And sigma is not the specification, that's the synthesis goal. Okay, let me give you now a concrete target example right away to try to give this a little more grounded. This is just a target example. And it will also allow me to talk a little bit about some of the extensions that we need to put on top of this very basic framework in order to get things rolling. Imagine I want to do web page synthesis and have a repository component that can construct various forms of web pages here. Since I'm a coffee lover, I'm saying I wanted a web page for my chair at the university, and there would be different ways of representing ordering coffee of various sorts. So for example, up here, I have some buttons that I can use to select. Here I have a drop-down menu, and here the layout of the whole thing is a little more simple. Okay, so imagine we have some collection of components here, written in Java in this case, with Java type shown here. My combinator symbols are custom form, and then it has a Java type drop-down selector, and it has a Java type, and so on and so forth. And so that's my repository, and at the theoretical level, it's a combinatory basis, or a set of combinatory symbols and types. Those types, those Java types, which are implementation types for the combinators, you have to imagine that behind the combinator names, I mean, these names refer to some components that are actually implemented somewhere else, but they're not as it part of the composition. At this point, we only care about composing these combinator names so that we get a website result. These Java types, implementation types, are also often called the native types. You see there in black. There, of course, they're not enough to say anything interesting about what we really want. And so here we make an extension to the system, going back to a very interesting type system called intersection types that was developed in Torino in 1980, and it's been studied ever since, and has an extremely interesting theory, and it turns out to be incredibly expressive and yet very, very simple. Because the core of this type system is really this intersection operator that you can see up here. What it really gives rise to is what I would call a multi-dimensional type system. That means any element in such a type system can have a finite number of types, not just one type. And we can use this here to introduce or superimpose these blue types, which I refer to as semantic types. Those are kind of application-specific semantic annotations with a logical meaning, because we're still using the arrow and we use this intersection type algorithm that have a logical meaning. So for example, you can see here that the string argument to the custom form combinator takes on the description of the title. And the Java.net URL is a location where a logo can be found, and so on and so forth. So these blue types are governed by this intersection type system, which I'll not show you, but I will follow the time here. But they're very important. This is really a key idea in CLS, is to use these intersection types as a way of endowing implementation types of combinators with semantic descriptions that are pertaining to the nature of what these combinators are supposed to do from an application-specific perspective. And so with that, let me just move on and then show you what would come out of it. This is actually a run that we did with CLS. You can see the interpretation problem is sort of indicated here. So our gamma is this now, black and blue repository with a bunch of combinator names and types. And we ask, can we find a combinatorial expression that has this type here, which gives the top level semantic type of an ordinary. And up here to the upper right, you can see that there are 4 solutions, 1, 2, 3, 4. Those 4 solutions are combinatorial expressions that compose to that type out of gamma. Now, you might say, okay, so functional composition, that's really extremely simple. Can we do anything interesting with that? Well, really, the answer to that question is that our combinators are typically method programs. They are programs that, when they get executed, these are purely functional combinations of our combinators, but when you execute them, they generate code in a possibly different language. So, for example, here you can see the keyword Java is used. What I show you here is, technically speaking, we would call that an embedded DSL to the functional programming language Scala. You can see we have the keyword combinator up there. And so you should now think of these Scala combinators. Those are the ones we really work with. And they don't necessarily directly implement the functionality we want. They may do things like code templating, for example. They may take a piece of Java code with a hook on it, and then another combinator might deliver another piece of code that is built into that. So we didn't build code, and our combinator are typically metaprograms. Here you see the semantic type application that I showed you before. That's now in the DSL one. The whole thing is integrated with bits. There's a lot of nice stuff around that which I can't go into, but you can load the repositories to the bit, and you can ask an habitation question that triggers the synthesis, right? And here you see the result list here coming out, and that automatically gets fed back into the Git repository of solutions in this case. Okay, I want to say just one more very quick thing about the expressive power of this whole thing. So, going back to this SKI theory of shrinking, I said before, we're not really interested in that minimalistic theory, because what we do here is that we view combinatorial logic relative to any given collection of components. So it's a much more general problem that we consider. And it turns out that actually, even with those simple types that I showed you before, which you might think are so simple as not being able to express anything interesting, it actually turns out that this inhabitation problem, that is, that there exists a combinatorial expression having a type from the repository gamma, that turns out to be undecidable. Because what it really turns out to be is, it turns out to be the provability problem relative to any given proposition or theory. And we know by classical results from the codes that this is an undecidable problem. There's a nice theory in terms of automating Turing machines for how to actually do the synthesis. We have a lot of complexity theoretical results. I'm not going to go into that, but I'll just leave them in the slides and for you to look at if you're interested. I do want to say this, that vis-a-vis this impressive list of high complexity classes, in practice that's not the real problem in my experience, because essentially you can use these types, not these intersection types I showed you, to actually program the composition. So that you can use your type annotations to really control the combinatorial explosion which is in there in the worst case theory. And also, of course, we've done a lot of algorithms engineering to make this somewhat efficient. Okay. So that's the first part. What I see this, I hope that I can give you some impression of what the background here is without going into all the details. This is what the CLS framework really looks like. So you've got, to the lower left, we've got a component repository in our Scala extension. As I said, those are pure combinatorial symbols with interface types, and they refer to some implementations in Scala that wrap typically code in other languages, maybe like Java, for example. Then there's an input goal type. And then we've got the heart of the composition engine, which is the habitation algorithm for combinatorial logic with intersection type. Out comes, not say Java programs, but out comes combinatorial method programs, those are trees, right? And so we can use the tree grammars to represent even infinite solution spaces using tree grammars to represent the set of all combinatorial expressions that solve the request. And then when you execute those programs, those combinatorial programs, when you execute them, they generate code in possibly some application. In this case here, I wanted to also mention that there's now a Python version, which is important for technical applications. You might ask, how can we use Python because Python is non-type? Yeah, well, we can use these semantic intersection types to say anything we want about the Python component. in terms of type expressions, and you can also use type annotations, native type annotations on your program, on your Python programs. Another comment here at this picture is part of the philosophy of CLS that we don't imagine being able to specify all possible properties of interest. Our input goal types are not necessarily to be thought of as complete specifications of the problem we want to solve. And this is important to me because I don't believe that we will ever be able to do that. Take something like, for example, performance properties of the generated programs. Okay, so we don't know how to specify that sort of stuff in the logic. So the philosophy of CLS is we try to specify sort of the structure at the level of types of what we want, and then we generate all possible solutions to that request, and that may be many solutions. And then we go to the right end of this picture here, and for example, filter those solutions. For example, using test cases, like we could feed those solutions automatically into the test suite, and we could, for example, choose the most performant programs that came out of this process. So you see, there's a conscious sort of division of labor between what is specified up front to the left and what is filtered out later to the right, which I think is important. Another thing that I think is interesting about the CLS framework is that it's easy to extend. So there are at least 3 natural points where you can put in various extensions, and we've also done that in applications with CLS. So to the left, you can think of trying to automatically configure or even generate some of the combinators that we may have in the repository. Or you can think of configuring certain parameters that enter into those combinators. At the mid-level, you're at the level of the ground. We can perform transformations on the ground. For example, let's say, just to take a stupid example, that I have an identity operator, I, in my repository, okay? And then, all solutions of the form I, or some X, they're all the same. And we'd like to filter those out. And we can do that using algebraic transformations on the resulting combinatorial ground that recognizes the trees in the middle. And then, as I said, at the right-hand end, you can put in filters and constraint solvers and whatnot. And so this is important to me also to say that I don't think of CLS as sort of the ultimate answer to some sort of very fundamental question. I think it is, but in terms of practice, I see it as a very useful way of also putting in other technologies around this basic motor that allows us to automatically compose things. The whole thing actually started by some ideas I had on putting together programs using architectural taxonomies shown here. This is a connector taxonomy shown down to the left. And I wanted to use that taxonomy to automatically generate connectors. And that taxonomy can be, those taxonomies can be mapped into the type system very easily using these intersection types. This is, again, an important methodological point which I won't have time to go into. I think the real strength of CLS, generally speaking, is really the automation of software product lines. That's the way. That's where I really see the strength of CLS, where you are able to generate whole families of variants of applications. This is important also later on. We can generate CLS in a very natural way whole families of applications that have some structure in common. That's a product line. So you can use it to automate software product line. We have a great collaboration with George Hyman, who's an expert in component software, where he used CLS to automate a product line of solitary that we have. We also used it early on to generate PPM processes that we use to control over long-storm robots. And here I've shown you to the upper left, this black structure is a sort of a taxonomy of insects. Now you can imagine that being transported into a taxonomy of robots. And it turns out that we can very easily represent that in our type systems. Here's a little wrap-up of this level of what I think are the pros and cons, but let me move on to what I now really want to say, spend the rest of the time talking about. Namely, some of the applications that we've been able to do in the last few years in particular, in connection with a graduate school, so-called Algorithmic that I've been running since 2016. It's going on until 2025. And so this is really something that I'm quite excited about. So I'll see if I can spend the rest of the time talking about some of those applications. The first application we did was in the context of planning building projects. And what we're doing, we're using CLS to automatically generate PDM plans to achieve something like ad hoc planning. So then we'll have some components that sort of contain knowledge about what is usually entering into certain kinds of planning projects. And you have a plan, you're following the plan, but now something unforeseen happens, and you need to change the plan. And so we were able to use CLS to do that, generating these the PDM plans, which you may or may not know, but they're kind of what underlies the critical path method in project plan. What you see here is taken from the debugger that is part of the CLS framework, where we can follow in real time how CLS constructs solutions to requests for composition. And so you can see that we can then go in and also take a look at why a certain result was the way it was, how did CLS arrive at it. And here's an example of an output coming out of that. We then turned to sort of more industrial applications, and the whole slew of applications almost that I will now end speaking of, they really focused on an idea that I think is interesting, namely that we could use CLS to generate variants of simulation models, and thereby try to contribute to something which you could call automatic design space exploration for technical applications. And so we had in collaboration, we had a great collaboration with the company Dortmund, which is a market leader in sheet bending machines. It's not Trump, it's Trumpf. And so we started working with Trumpf on trying to generalize a simulation model for a factory that they use, so that they wouldn't just have one model, but they would actually be able to automatically generate variations of that model. And maybe it's interesting to reflect on why Trump was interested in something like that. The way they use simulation models is actually in sales. They produce machines, and maybe they also use simulation in the construction of their machines. I don't know. It's a very high-tech thing. Sheet bending is very high-tech stuff because it involves advanced laser technology, for example. But this factory model that they have is one in which they are able to, play through various scenarios with the customer and try to figure out what kinds of machines this customer should buy, and how many, and so on and so forth, and how it should be organized. And you can already hear that I'm telling this. If you feel like creating variants here, right? The more you can variate these scenarios, the better you will be able to advise the potential customer. And so this is something we've been doing with Tom. I just need to get my somehow. Okay, so I think I'm back on track here. Okay. And in the context of this work, for example, we had occasion to introduce various constraint solvers that would filter out unwanted variables that didn't make any sense. But again, following the philosophy from before, we are prepared to generate more solutions that we want to implement because we just filter them afterwards. This is what the industrial use case looked like at the beginning when we started a couple of years ago with Tom. And what you see here is this factory situation where you see some intra-logistic objects in sort of a factory hall. And then the idea is that you can put some trunk machines into that context and see how that plays out. There's a trunk model library which was constructed by Bosch actually, or Dortmund Bosch, which we used, and we essentially managed to, in rather short time, wrap this library into CLS using, in the first round, we were using a kind of a spreadsheet-based model that Trump already had for like composing these things, but it was all manual, right? For example, we drag and drop on various components of the simulation model. You should know here that simulation model is very stuff. I mean, simulation model software, right, is something that most of us would not want to write, and put it that way. And so what we did was we systematically tried to identify points of variability in these simulation models. And for example, we do an analysis on the order of magnitude of variations, machines that are different, the cutting speed, assembly space, height of loading and unloading of material that connects them to the intra-logistics of the concrete situation. In that case, there were 18 possible configurations. Bending machines is another kind of machine that you may use. They have configurations. If you multiply that all up, you already think in some of the core scenarios it's more than 10,000 different system variants. And we automated that using CLS and actually followed the sort of product line, the classical product line software engineering methodology in getting the CLS ready. Here's a view of the repository describing various bending machines. You can see the intersection types there, capturing various sort of taxonomic concepts of interest from the domain, making sure that we generate solutions that have a good chance of being interesting, but still being willing to generate a superset of solutions that we then need to figure out. In this case, the code that we generate will be the XML code. We are also again using the meta-programmatic features of CLS in an absolutely essential way. We then did experimental results. We were able to measure various KPIs coming out of the generated simulation models, and of course that leads you to then being able to select the best model, the best configuration for a certain scenario. That may of course not be one best solution, in which case you're going to want to compute some sort of Pareto front over the generated solutions. Here's another take that I think is methodologically very important, and which was very pleasing to me in working on this project. This is still Trump, but we went further, and we just published now paper with them in the Winter Simulation Conference. The point I'm trying to make here is that we turned out we were able to, within 3 months, to take an existing complex, highly complex simulation model and actually making it CFS active. That means wrapping the components and bringing them into CLS so that you now have the generative power of CLS working on the code, working on the components, and thereby generalizing the originally existing one model, the whole family of models. So the way to think about it is take an existing model, you say this is an interesting component, this is important, but couldn't we vary the component? What if we wrote the logic in this, let's say, control component a little bit differently? And what if, where at this place there's a component that stands for a particular kind of machine? Well, what if at that point we were to stick with a different component representing another kind of machine? You can see in that way we raise the level of variability and we automate that variability. And here you can see a screenshot of something we just generated not very long ago. You can see in this case we also were able to take more and more into account of the materials and logistics around these machines. These blue lines that you see there, they are pathways for workers to move around when they operate in machines. And we see here 4 different scenarios using different kinds of machines. Those machines are these brownish things that you see standing sort of over and underneath this blue-red line in the middle. Okay. So that's sort of this whole direction of trying to apply CLS to the generation of variants of simulation models. Once you have that idea, it's a very close step to start thinking about using this technology to train AI systems, right? And so there's a big topic in AI nowadays that is about using various kinds of models, including simulation models, to drive and scale the training of AI systems. And we did an interesting experiment or application of this idea in the context of sample-based motion planning, which is used in robotics. And the basic architecture now looks like this. So we're now closing the loop with CLS in that we bring in some kind of stochastic model after the test suite that will allow us to do some sort of learning. You can see that the stochastic model may influence the way CLS chooses to generate solutions, but it may certainly also generate it may have an impact on what components we select or how we configure components. That may come out of the stochastic model. In this case, this is actually what happened. We build a feature space, and we built an optimization problem around that, defining this design space for motion planning programs, and we componentize those plans. It turns out that this whole field of motion, sampling-based motion planning, has sort of a natural component structure. There's a natural family of techniques and heuristics with various kinds of parameters that work with various kinds of planners. So, for example, a certain kind of planner needs a certain kind of rate. There are parameters pertaining to compute time, how long can the task be that this planner is doing, and so on and so forth. So these planners, they actually make out a natural family. And we were able to capture that in CLS, putting in something called Algorithmic 2.0, which is a design space exploration systems. There are some other people wrote, Luke from Stanford wrote that in order to explore design space for sort of low-level computer science. And that turned out to work pretty well here. And what this thing is doing is it's actually now driving the process. The high number here is now computing the Pareto count over various generated planners, and so we can evaluate those planners using simulation technology again, which is also code-generated planners, right? So we generate planners and there's a scenario, and we then automatically are able to generate the simulation that is then used to evaluate various KPIs for those planners building this Pareto fund that is seen down here. And again, just to show you that I'm not lying, the whole thing was driven by a combinatory repository shown to the left in just some examples using intersection type annotations on the combinator sites. I mentioned that one point that CLS requires is, of course, it requires you to build your repository. That may take some time, so it's an interesting problem to try to bring down that time. We did that in a project that had to do with logistics, where essentially we started the problem of trying to automatically start certain parts of the repository. I'll just mention that at this point without going into too many detail. This is an example of doing something to the left there in our vision report. Here's an example of an application that I really thought was
sorry.
So after we did this sampling-based motion plan stuff for robotics, if I have 2 minutes at the end, I can show you a cool visualization of some of those motions that we are able to generate. But here's something I have not
Can you see me?
No, I'm not seeing you.
I'm sorry, I must interrupt you a little bit. We have to discuss. We need some time to discuss a little bit, and time is over.
Okay. I have a hard time hearing you, but let me just wrap up then, okay? Let me see if I can wrap up. And now I have to share my screen again. And I hope you can see it again now.
Yeah.
Okay, it turned out, this was a surprise, I have to tell you that. It turned out that we could use this way of generating variant motion plans to control machining operations. Like now you're looking at a scenario where you have some sort of drilling machine, okay, and the objective is to remove material from some block of material, for example, some iron material or something like that, or whatever. And as you can imagine, that's a highly technical thing. And how you move that tool around that material is very important for a whole lot of KPIs, like how fast does it get the job done, how much heat is generated. There's a lot of physical parameters there. And we could use CLS to actually automatically explore the design space geometries and movement controls that we could use in this context, and then we could use simulation to evaluate them. Here, right at the end, a couple of other pointers. An interesting application that just got started is synthesis of algorithmic families. Here, in this case, for scheduling problems. And CLS is here being used to compose different kinds of algorithmic strategies, like, for example, heuristics. And it turns out that in scheduling, there's a fantastic family of algorithms that we can go and component engineer with CLS. Decision pipeline synthesis is another topic that is in the works, and also again that it gets into the topic of using CLS to drive AI applications in this context. So I think with that, I just wanted to say thank you for your attention and wrap up. I think there are many industrial applications that we're getting in touch with. In particular, after we started thinking of CLS as a generator of families of simulation models, it turns out to work pretty well in practice in complex real scenarios. Because we were able to take, for example, an existing model and then gradually turn it into a more general component-based model for generating variables. And it turns out to be pretty easy to use. I've been able to make many bachelor students productive in some projects. And I already mentioned some future reflections around model-based for AI. With that, I think I should stop. Thank you.
So I thank you very much, Jakob. There is time for a short question or two.
Hey Jakob, this is Bernhard. Thank you for the nice talk. Can you hear me?
Yes, I can, but not all too well.
Okay, maybe I come closer here.
Yeah.
So again, this was a great talk. I have one specific question. Your work that you published in the CIRP proceedings, we also in our graduate school used that as a publication way. This is very interesting because it allows to digitalize some of the issues that you have in production pipelines. Yeah? Did you compare your construction approach with other programs and techniques that are available in that community?
Yes, we did. The last paper I mentioned is actually an overview paper where you can go in and we did a literature study there. I think generally it's a great area to be working in because there's still a lot to do. So what I think you find generally is that, the people who write this sort of software in the production context, as you say, they're not typically very informed in terms of informatics and computer science and software technology. Actually, they're more like classical engineers.
That's also my impression.
They would not get these ideas that I've been talking to you about today. They have. Yeah, so maybe I'll set this back as a provocative.
Thank you. Let's follow on that in another models. Yeah, thank you.
So are there some other urgent questions? This seems not to be the case, so we thank you again. And we wish you all a quick recovery and we are very...
Yes, thank you. Enjoy the day, everyone. Thank you.
Okay, so see you.
See you.
Bye. So now we have a short break for coffee and we reconvene at 10 minutes after 11. Thank you. Decentralized.